We're going to go from one of the greatest scope scientific challenges at which mathematical modelling has been thrown to a much more specific mathematical issue, but nevertheless a very important one, particularly looking forward to greater uncertainty in future power systems of demand forecasting. And I'm delighted to welcome Andrew Richards from National Grid, and also a recent PhD graduate of the probability group at Heriot-Watt University to speak on this issue. So, Andrew.
Am I switched on?
I think I'm switched on now, and I hope you can hear me. I'm one of the four demand forecasters at National Grid, or at least I was until yesterday afternoon, when I was somewhat disturbed to hear my boss, Chris Murray, say that demand was now a given, and Janusz also very kindly said that demand is deterministic, not stochastic. So if that's the case, I probably will find that I've got a new job when I get back to National Grid tomorrow morning. Just a quick few words. This has been said before, but it just so happens to be the first slide of my presentation. Why do we need to forecast demand? Because electricity systems are, by their very nature, self-balancing. Whatever power you put in, you will get out at the other end, and there is absolutely no trouble about it. The only problem comes if you determine that you want to maintain the frequency, and it's the frequency rather than something like the voltage which is really important to us at the control centre in National Grid. We are supposed to maintain the frequency at 50 hertz. We are allowed to go up to 50.5. So there's some room for flexibility. Our operating procedures actually say 50.2. If anything goes above 50.2, reports start getting written. A bit higher up at 52, generators start tripping, we hope, because if they don't start tripping, then what happens is they spin too fast and they come out of their casings. And it's never happened in this country as far as I'm aware, but not to a big machine. But it has happened, and it is pretty catastrophic. So it's something we're rather keen to avoid. Going the other way, if we find that demand is greater than supply, the frequency goes down. It's like, I know there have been lots of analogies, but it's like driving a car up a hill and the engine you haven't changed gear, and the engine is really beginning to struggle. 49.8 is where we like the bottom to be. 49.5 is the lower statutory limit. 48.8 is when we start disconnecting large amounts of demand. That happens very, very rarely, although Janusz mentioned the event in 2008 when we did have to disconnect some demand. But again, these are very, very rare events. At 47.0, demand disconnection complete sounds as if everything's under control. It's under control in the sense that nothing is on. The system is stable, but it's reached a rather unfortunate equilibrium. So that is something, again, we're very, very keen to avoid, and it is essentially the same as a car going up a hill. You haven't changed gear and you've stalled. That's what happens to the machines. That's what a typical demand curve might look like, except that is not a typical demand curve, because that's the 23rd of January 2007, which is when we got the largest ever peak demand up there, round about 58 point something gigawatts. But despite the fact that it's a very large demand in our terms, I think this winter we hit about 57.8, I think. So, it's not ridiculous, but that is the biggest one we've ever had. The shape remains roughly understandable here. This is the low overnight. People starting to get up in the morning, getting ready for work, taking the kids to school. You get a peak here, a slight drop off, a lunchtime peak, people sort of dozing a bit in the afternoon or not running their computers quite as fast or something. And then this is winter, so people go home and they do two things when they get home. They turn the kettle on and start making tea, and they turn all the lights on because it's dark. And then during the course of the evening, things just die away. I think that's one of two things. That's either a random fluctuation, or it is possibly the result of some tariff given to maybe an industrial company for overnight working. There used to be a very big effect of something called Economy 7 coming on at midnight. So it could be one of those, I'm not sure, but it's unlikely to be a bar, at least one bar. This is England, Wales and Scotland. So the forecasts are done aggregated for England, Wales and Scotland. It is GB. We don't do Northern Ireland. They're now integrated more into the Irish system. You can see that this graph here has been produced on minute by minute data, and it's a bit wiggly. There's noise in there. If you looked in closer, it would get noisier still. The noise isn't particularly useful for us because one of the things, not the only thing, but one of the things we're interested in is peaks, and when you've got a lot of noise, the peaks aren't necessarily exactly where you might expect them to be. So we just smooth these out over half-hour integrated periods. That's a good time scale for the control room to work to at the moment. So it's chosen for their preference rather than the preference of the mathematicians trying to do the forecasting. It may be that in the future, with increased variability of supply, we may move to 5-minute periods, but essentially at the moment we work with half-hour periods, and that causes us some problems at times. So that's what I've said there. The minute history, it's noisy because at shorter intervals you can see more individual behavior. It's also because the rapid response metering, there are all sorts of different types of metering which provide us with our information. If we want second by second information so that they can control the system well, you have to pay a cost, and that is that it's not always accurate. If you want really good data, know exactly what's going on, you have to wait about 6 weeks for settlements to get through, having agreed with all the distribution companies exactly what's happened, and then we get our most definitive figure, but it's a little late for the control room. As we saw the other day, 2 minutes is the sort of time scale. Once you start getting frequency collapse, that's the time period you've got to do something about it, and 6 weeks is not really very helpful. So we work with this half-hourly data to smooth out the demand curve, and we may move to 5 minutes resolution later. The demand curves, well, it's not very surprising, but this illustrates it. The top curves here are a week's worth. I think this is the winter of 2007. That was the demand across 1 week, a week in January, I believe. I suppose the things are that these 3 days here, which are Tuesday, Wednesday and Thursday, look fairly similar. I can see, because I'm used to looking at these, that the Monday is a bit different. Monday is always slower to get going. So we try very hard not to make judgments and have our explanations sort of harden too much into what we think of as reality. But I know very well that the British public don't get up that well on Monday morning, and everything takes a bit longer to get going because that always happens with the demand. Equally on Friday over here, the slope is always much shallower after lunch. That is always the case on a Friday. It means that when we're trying to look at historical data to tell us what we think might happen on a Friday, you have to use a Friday to compare it with. It's no good using a Thursday. Because the shape is different, and obviously the weekends are different. I was interested in a slide that Sean showed from Illinois, which showed, as far as I could see, a Friday, Saturday and a Sunday, and they had very high demand on Saturday morning, and I was very surprised by that. look really quite high, whereas on Saturday morning here you can see that the demand isn't that great. The curve underneath is from the summer of the same year. I believe this is June 2007, a week, and there are some differences which we'll talk about in a moment, but the main message there is it's much lower in summer. It's no surprise, but that shows you what the actual difference is. So how do we go about doing this forecasting? What the purpose of my talk really is to ask for some help, both with what we do now and with what we are going to have to do in the near future. But it doesn't make much sense to ask for that help until I've shown you exactly the sort of procedures that we go through and how we think about things at the moment. We know that the weather is going to have a lot of effect on demand. So we've got some weather variables that we get from the Met Office. We get given them every hour, but it's not actually very useful in terms of modelling to use each hour, because in terms of modelling we're looking towards the future to do some forecasting, and the actual information comes in every hour, but we only get forecasts at 5 in the morning, 8 in the morning, 12, we get one at 1500, 1700 and 2100. So there are only intervals during the day when we are provided with forecasts. No doubt we could get more, but I think the Met Office would charge us a vast amount. So like everything else in business, it's a trade-off between scientific knowledge and cost. We use, not surprisingly, temperature, but we don't use spot temperatures. We average them over the previous 4 hours. We have a strange temperature measure called effective temperature, which we use because one of the things that is very important, especially in winter, is heating in buildings. Buildings have a heating lag. It takes time for them to heat up and time for them to cool down. We model that by saying that what we'll do is we'll calculate a temperature measure based on the observed temperature over the past 4 hours and this effective temperature 24 hours earlier. So we take into account what it was like yesterday and what it's like now, average that out, and that seems to work quite well for us. We use both wind speed and factor here the cooling power of the winds, essentially a wind chill type factor. The wind speed has been interesting over the past 10 years. It used to be the case, always, that when the wind blew in the winter, people felt cold, and so you knew that when you got high winds, you would have higher demands. About 5 years ago, that relationship started to weaken, and it's now the case that when the wind blows, we have lower demands. And the explanation for that is we have a lot more wind generation, nowhere near what we're going to have in 10 years' time, but we have a lot more wind generation. Only large wind generation plants are directly connected to the grid and have to provide us with metering. Small little plants, a few turbines stuck up on top of a hill, can connect directly to a distribution grid. They have their own metering where they settle up with the distribution company, but we don't see it, and they've got no legal obligation to tell us how much they're generating. So we have metered wind that we can see, which is part of our supply, and then there's all this stuff that we can't see. It's invisible, which is the embedded stuff. And the embedded stuff, from our point of view, then, is negative demand. We build it into the demand models, not into the supply, and we model it very crudely at the moment just by a linear function of wind speed. It works at the moment because there isn't that much, but it's going to have to change as the amount of embedded increases. We're going to have to be much more sophisticated about that. And then we have something which we calculate from radiation measurements that the Met Office give us. It's particularly important in summertime, the illumination. The problem we have with it is the Met Office aren't very good at forecasting it. Again, somebody mentioned it in the a previous talk. A lot of it is to do with cloud cover, exactly how much radiation is going to get through different types of cloud, and that's very hard for the Met Office to model. So it's very hard for us to say exactly what effect is going to happen. 2 weeks ago, when I was doing the forecast on a Tuesday morning, I was expecting demands at a sort of reasonable level for a Tuesday morning, and suddenly they started coming in about, well, I could see as we were ramping up towards 9 o'clock that things were going to overshoot by a significant amount, and I started sort of ringing round and found out that the forecast, I can't be entirely precise here because the only way of talking about it is in our numerical scale, but I had a forecast for illumination of 7 over London, which is really quite bright. It was as if in London that day the sun hadn't come up, and the measurement was -70, and in a sort of linear model that actually makes quite a large difference. But once we took that into account, things became more normal again. Temperature. I've said here this is the idealized effect of temperature. This is just taking how the temperature works in the linear model at a particular time of day. By the look of it, this is probably around about lunchtime, I would think. When the temperature is low, demand is high. When the temperature is high, the demand starts going back up again because of essentially sort of air conditioning units. And papers and things like to tell us that at this point here is the temperature the British public like to be at. I'm not sure it's that interpretable, but that's essentially the type of temperature demand. And illumination, this was a nice slide that somebody found. 2 successive days in 2005, September I think, where the weather was very, very similar, and they were both sort of midweeks, so they had the same sort of shape, and you can see the shape is exactly the same, well, not exactly, but very, very similar there. And then this patch of cloud and rain comes in from the west, spreads across and moves there to, that's about 5 o'clock in the evening I think. And the demand on the day when it was sort of dark and rainy, it's not surprising, but it's much higher until the cloud passes and it just goes back to being normal again. What else do we take into account? Different days of the week we have to look at which year we're in. This is very crude, but it turns out that being crude here is the best thing that we've found that works. We want to take into account economic factors. Over the recession, we saw very, very, very quickly that demands were down. We have tried modelling all sorts of things to give us a good idea of how much we should expect. We haven't found anything better than saying, let's look in the past and just say over a year, well, it's actually over 6 months because we do summer and winter separately. But over that 6 months, the economic effect remains constant. That's the best we can get for that. Time of year, something I'm worried about, but we have essentially the beginning of British summertime, we call the first day 1, we call the second day 2, we call the third day 3, and so on. And then we model where we are in the year by some polynomial in R. And we're also building in sunrise and sunset into models, although they haven't been used in the past. How many people are on holiday? We would love to know that. So we use this as a proxy, the percentage of schools on holiday. That gives us 2 effects in one, really. The effect of schools heating and things, lighting being turned off, but also percentage of school kids on holiday gives you a proxy for the percentage of families who take time off work and go off and either abroad or go camping or whatever. So it definite effect on the demand at certain times of the day. Annual holidays, we have sort of indicator variables for common holiday weeks. Bank holidays have a huge effect, but we don't actually build them into the model. We rather exclude them from the modelling process and then when they come round we sort of deal with them in an ad hoc basis. Other things that might affect us we also deal with in an ad hoc basis, things like spikes from television programmes and sporting fixtures and the 2-minute silence in November. All those we just say we'll take a representative look at what happened in the past and make an educated guess. So you've seen the shape of a demand curve. That shape remains fairly constant over a short period of time. Over the course of a couple of weeks, Mondays look like Mondays, Tuesdays look like Tuesdays. It evolves as the year goes on, but it evolves slowly enough that we get some consistency, we get the same sorts of turning points in the curve, we get the same sorts of points of inflection in the curve. So we identify those turning points and points of inflections, we call them cardinal points, and it's those cardinal points that we try and model. We then, having got our cardinal points, sort of do some interpolation in between them. To show you that this claim that the shape does remain constant enough, what I've done is I've collected together a whole load of demand curves. They're all from Tuesdays, Wednesdays and Thursdays, which are similar shaped days. I've scaled them so that the maximum and the minimum are at the same point on the graph to take, it doesn't entirely remove the weather effects, but it makes it more understandable. And the eye tends to focus on the shape of the curve. That's the first one. I'm not able, because I've done this stretching, to put a scale here, but this is sometime in January. And from day to day, as we move through, you can see that it does change, but the claim that the basic shape remains the same, isn't okay, is fairly good. But what has happened? What has happened is we've moved into British summertime. Before we move into British summertime, this thing here is what we call the darkness peak. And as I said earlier, two things are happening at the same time. One is that people are coming home from work and getting their suppers ready, and they're turning the lights on. Just before it changes, can I get it? Yeah, you get this sort of little kink occurring. That kink there, it's just beginning to separate out into two peaks, and the government have got British summertime in the right place as far as I'm concerned, because that's just before we change. They can see the little kink coming, and then they move it, and those two peaks separate out into two. This bit here, once we get into summertime, is a nightmare. That's the coming home tea time peak, that's the lighting up peak, that's the trough in between. And if you watch them, it's the most volatile part of the curve. And that particularly that peak in between the two sort of goes the trough in between the two goes all over the place and sometimes completely vanishes. It makes our job difficult. So what we do is we divide this up into early morning, up until about sort of 6 o'clock in the morning, and then morning, afternoon, evening. And we define points, the minimum here. It's hard to see here, but there are often two maximums, one at about 9 to 10:30, one at about lunchtime. There's a trough, there's an early evening peak, a trough, a late evening peak. And to patch the curve up, we take a few fixed points as well, and that's the picture that we get. The top curve there is a typical winter maximum. That's a typical winter's day underneath, and there's a little peak there which is called the 1A. This is in period 1. The first peak is a 1A. In winter we have this thing here which is always at 3 o'clock and at 4 o'clock, and the 1B is the trough. 2A is the little peak up here at roughly speaking 10:30. It might be there So that's for Saturdays. That's a bit different, where we put it in at a fixed time. That's the 2A peak. There's another lunchtime peak about here. It looks like they're always level there. There can be quite a trough in between the two. 5:30 in the afternoon is 3B. Sorry, 15:30. I always do that. 15:30, 3:30 in the afternoon. There used to be a 3A, but the tariff that made the 3A disappeared, so we don't have it anymore. The darkness peak, and anyhow, those are our cardinal points, are the things we model on. Once we've got the level of our cardinal points, we look back in history to find a day that is similar in terms of its weather, and then we essentially just say the historical day will give us the timing. The timing is a really difficult thing, and we don't know how to do this. All we do is look at one day and say we'll just copy the timing from the historical day to our forecast day. I would love to be able to model not only what we model at the moment, which is the height of these peaks, but I would love to be able to model when they come. The difficulty is that we have got these half-hour periods, so they're going to come in one of it's a discrete type of modelling rather than a continuous type of modelling, and we have to actually say it is going to be at this time. We can't say the probability is going to be that it might be here, it might be here, it might be here. We need to give the control room a time when they might expect this peak to occur, and the discreteness of it seems to cause us difficulties, and we've not been able to model it successfully, and we would love to be able to. So that's the first thing I would like to be able to do, is to model the timing of when these cardinal points occur. We then assume that once we've got the timing, that the shape of the curve in between will just look like the shape of the curve on the historical day, and we do some sort of affine stretching transformation to match it on. And we would like to be able to do that better. It would improve our current methodology. But saying we want to improve it, I want to tell you how well we actually do. If we look at the peak of the day, that is one of the things that the control room are interested in. What's the greatest demand tomorrow that we're going to have to provide for? Our mean absolute error on that is just over 450 megawatts. Out of a demand which might be typically in winter 55,000 megawatts. So we could do better, but it's not bad. Typically within day, mean absolute error for different cardinal points ranges from about 250 to about 450 megawatts. So you're closer in time, but some of the points are more difficult, particularly that trough that you saw there is difficult. When we do our interpolation process, we get much less good results. In a world of greater uncertainty in terms of how much supply we're going to get from the generators with wind, we would like the half-hourly predictions that we do to be much better until smart grids come in and do whatever they're going to do. I'm still not convinced I know exactly what it's claiming they're going to do, but we would like to improve this, and that is something that we are going to have we are thinking about very actively and trying to find ways of getting that better. And it may be that we have to ditch our cardinal point methodology and go for something else, or it may be that we can find some way of adapting what we do at the moment to getting what we want. At each of these cardinal points we have different models. So the model for the peak at 9:30 doesn't look anything like the model for the peak at 12:30, although there are similarities, I suppose. Because of that sort of discontinuity that we saw going from GMT to BST, we have different sets of models for GMT times and BST times, which means we do our whole remodeling process twice a year. We construct models of different sorts. One is a sort of standard linear regression model, which I guess the guys who first did this thought of that as being the conventional statistical approach, so we call them conventional models. And then the way out wacky things where we take into account what's already happened. So we essentially do a sort of time series regression, which they call trending models. There are problems with our trending models mathematically, which I will talk about shortly. But if I knew how to model those properly mathematically, I think we could do a better job than we do at the moment. We have models, some of which work all the way through the week. They try then to take into account the different days just by having indicator variables for the different days. We have models that only work during weekdays. We have Saturday models, Sunday models. We have some weekend models. I haven't said that there. So on any day of the week, at any particular time, we usually have 2, 3, maybe up to 5 models that are giving answers, and the spread of those answers is our way of conveying to the control room how much uncertainty there is without using the word probability. We also know that if you take 2 days, say in summer, one in mid-June and one in early April, that have essentially the same weather, which of course you can get in the UK because of its sort of extreme variations in weather. Nonetheless, the demands can be very different on those 2 days, despite the fact that in all other respects they look the same. So we know that there is seasonality. So what we do is we have this counting variable, day 1, day 2, day 3, which is confusingly has always been called R. And we build a simple polynomial. So there it is. The 2b, L is because the software that we use to do the actual number crunching doesn't like variables to start with a number, and L stood for load. The load at 2b is modeled with for this one it's a cubic polynomial in R, indicator variables for economic activity in 08, 09 and 0910, something telling us what day of the week we're in. One of the reasons I like linear models, I'm sure I'm preaching to the converted here, but I like these linear models over things like neural nets, is that once we've got our model, it's not only going to give us a number, it's going to tell me something. This tells me that at 12:30 lunchtime, I have to take into account whether I'm on a Friday, a Saturday or a Sunday, but essentially Monday, Tuesday, Wednesday, Thursday are all the same. So that Monday effect of people getting up slowly, well, they've got to work by 12:30, which is comforting to know, really. The school holiday does affect how much demand there'll be at 12:30. It always goes down in school holidays, in case you're wondering if your kids are at home sort of on their PlayStations, really sort of putting on the bills. There's always a drop for school holidays. How much it drops by varies by the time of day, but if there's any effect at all, it will be negative. Some quite sort of complicated effects in terms of temperature, some of which are quadratic because of that effect that I showed you on the idealized graph. An illumination effect and a wind speed. They're typical sorts of things I would expect to see in a model like that. When you use an adjusted R squared as a simple sort of measure of how good you're going to be here, 0.984 is what we're getting with that model. And I worry about these seasonality terms because it's very easy to get artificially high adjusted R squareds and things by using seasonality. We can't do without them, but what I don't know is, given that I've got to have them in there, how I can judge whether there is anything sort of artificial going on or whether they're really telling me something. How do I know when I'm overfitting in terms of a seasonality thing that I've got to have in there? And if you look it up in sort of the standard textbooks, they say avoid this if you can. They don't seem to tell me what to do if I can't avoid them. So that's my second question. What do I do about seasonality in these conventional models? Our trend models, they're essentially just related to time series with regression. So ARMA models with linear regression, or linear models with correlated errors, just depending presumably on your point of view. And as far as I understand it, the standard approach that I ought to use is I ought to take the time series that I've got of demands. I want to explain something about that in terms of my explanatory variables u in a linear way. So the first thing to do is just to try and get some sort of estimate for what the linear explanation function might be. Once I've got an estimate for that, I take that away from my actual demand to see what the residuals are. I look at the structure of dependency in the time series of residuals to see what it looks like, if it's an AR1 or something. And then once I've decided on the types of things I'm going to put into the model in terms of explanatory variables, and I know by and large what its time series structure is going to look like, I then plug it into some nice bit of software which will use some sort of generalized least squares algorithm to tidy everything up for me. That's what I'm supposed to do. If I do that, I can get results, of course, but I can't get the best sorts of results. In that if we run that sort of model in parallel with what we actually do, it doesn't have as good a predictive power as what we actually do. Unfortunately, what we actually do is exactly what every single textbook that mentions this tells you not to do. What we do, we perform an ordinary least squares regression on all our explanatory variables, including the term that we are trending on. And that should not work. And that's what everybody says. That's what Box Jenkins says, and Chatfield, and so we just say, here's a trend model. We're trying to get the demand at 04. We'll trend it on the 04 from the day before. That's what that meant. We'll include the year. We'll plug in some temperatures from the day before, some temperatures from today, maybe some of them with quadratic terms, bit of wind speed. If we were using the sort of the standard methodology, what we would do is we'd come up with some sort of we'd have the demand. We'd essentially take off the explanatory variables to get the residuals, and then we'd get a time series structure for the residuals. And then when you sort of expand it back out again, it restricts the coefficients that go in front of these things. They have to be the coefficients from today compared to the coefficients from yesterday all have to be in the same ratio. Not doing that gives us more flexibility, which gives us a better fit in the past, and it seems to give us more predictive power in the future. So this is what I want to keep doing, because the job is for me to be able to give the best possible sort of forecast to the control room, not to do what I ought to do mathematically. But I would like to know why this works. I'd also like to know if making this approximation, is there a better way of doing it? Is there a correct mathematical way of building this sort of model? So I can then look not to see whether I want to know whether to use the approximate method, because this works approximately, or whether to invest in some extra technology to do it better. Yep?
Sorry, I'm not a time series guy, but when I teach this sort of stuff to the MBA students, I tell them that if you're going to do this, you're better off to take differences or ratios. Like the finance guys would do its prices, they
Yep.
buy the price directly. But I'm not quite sure how it really relates to the other time series.
It makes sense really in finance, doesn't it, to take these ratios, because you might think the underlying sort of physical reality is something like an interest rate. So to take
How about the difference? Just the fact that you take a difference or a ratio, it's trying to decouple. You've got a kind of a correlation going on.
we
here,
have
and it sort of tries to decouple that. Now, whether
there it
really
is.
works,
There's my partial autocorrelation function for that model. What on earth these high frequencies are doing up here, I don't know. But you're right, and we there are lots of things that I still need to try. But the more advice I get on what to have a go at, I'm really keen to try something to make this either, or to make it the better mathematical model, so I can see if it's worth the effort of using that in our predictions, or if I can say this is the better mathematical model, but we're within 0.5% of where we ought to be, so it's okay to stick with what we do at the moment. That's essentially what I want to know. So there's a question here. How do we correct the sort of naive and incorrect and 3 stars, never ever do this, and all the textbook warnings, so that we can see either actually in this case it's okay, or it's not okay and we can do better and this is the better procedure? That's what I want to know. Not all of our models trend on the same cardinal point from the day before. This is purely a practical thing. We want to use the most up-to-date information that we can, basically. Because of the type of approximations we're making, it would be nice if we trended on points that had the least residual error. So we look at points that have smaller residual error rather than larger residual error. We also need to make sure that these models can produce forecasts in time for the control room to use them. And the forecasts have to get there about 6 hours before they're actually going to be used in practice, so they have time to call up plants. So if I go back to this thing again, if I'm trying to give them information about how much they're going to need at the DP here, the darkness peak, or this tea time peak here, which is about sort of 5:30 or 6 in the evening, I have to give them that information at lunchtime. So it's no good waiting till this point here, seeing what that is and trending on that, because I've missed my opportunity. So there are no models for this that trend on values back here after lunchtime. That sort of reasoning means that that's how we do things. This is what we're trying to forecast. This is what we already know on this line here. So if I'm trying to forecast the 1B today, which is at 5:30 in the morning, I use the 1B from the day before. If I'm trying to forecast the 2A at 10:30 in the morning, it's okay to use the 4 o'clock one. I pick on this 4 o'clock one because it's quite a stable point. It's got small residual error. The next one, which has got small residual error, is the 2A, but I can't start using it till I'm up here. So the overall pattern of how our models sort of interact with each other is like that. And that's not a sort of standard sort of pattern that you might get from an AR1 or something. It's more complicated, and I don't know how to deal with it mathematically, and if anybody's got any ideas, that would be brilliant. How do we model these dependencies? I just wanted to give you a quick idea of how we use a model. That's Saturdays, actually, at 10:30 in the morning, the demand over 3 years. We just sort of tried to model that, for instance, on this 04 data. So that's the mean of those values. That's the 04 data, 4 o'clock in the morning. If we just try to do that, do some sort of linear model using that, there's clearly a relationship. We chuck in some extra stuff, the economic effects, the school holidays, the illumination, the cooling power, and it's suddenly beginning to fit reasonably well. It's the best I could do on that model. 0.96 for a Saturday was pretty reasonable. Somebody said to me yesterday, well, once you've produced the model, can't you just get a machine to do the forecast? What we do is we take our demands, we subtract off take our historical demands, say the demands from last year, subtract off the weather that we know that happened last year, subtract off the demands that we know happened at the 04, and we're left with this stuff here, plus error. And we plot that. Ideally, that ought to be a straight line, and it isn't. But that's what we actually get. Most of the time, it's fluctuating up and down here within 500. It's doing okay. That's your residual error, sort of just kicking along. And you've got to use that for forecasting. So the first day you come along, you've got to have a guess at where it's going to come in this year, which will be at a different level because you've got a different economic factor. So you guessed and you were either right or wrong. It came in there. So you've now got to guess what happens the next Saturday. So there you are sitting on a Friday morning, coming up to 8:45 when it's all got to go out to the market, and you're saying, where do I put the next point? Do I make it follow this curve, or, well, no, I'd probably go roughly there where it was before and hope to see what happens, and it in fact went there. My next guess was informed by the fact that I know something that you all know but you don't know you know, which is that that's Easter, and Easter is there next year. So that's what happened. And that's where it's interpreting the thing like that as it sort of fills in, that is where the forecaster earns a bread and butter and gets a bit of hair loss as they worry about whether or not they're going to lose their job. Where do we go from here? New control mechanisms for the balancing the system. Greater uncertainty in supply means the control room want greater certainty in demand. They want these half-hourly forecasts, which we're not good at, instead of or along with our cardinal point forecasts. So we want to improve our current methodology. I'm worried about seasonality. I'm worried about the dependencies of the residuals in the trend models. And just generally, what other techniques can we look at? Neural nets, I don't like, but I'm quite happy to use them. I don't like their black box. I'm not letting you know what's going on inside. What else is there? The sort of fractional time series models and things. I don't know. Thank you very much for listening to me.
Right, thank you, Andrew. So we're running a little bit behind time, so
I'm
can
sorry.
we take a couple of quick clarification questions while we're doing the changeover to the next speaker?
Yes. Are your forecasts or similar forecasts used for setting pool prices? And if so, is there any feedback? If you predict a peak triad, then customers are meant to respond to that.
We don't predict triads, but our forecasts go out to the market, and they are the things that lead to the price setting mechanism. Presumably, as suppliers say, we think the supply is going to be, the demand is going to be up here, so there must be some feedback. Yes. Do I think it's significant? I hope not.
One more quick question.
Andrew, I was involved some years ago in using what you're calling trend time series analyses to help supply companies to predict what the demand was going to be from their customers. And as far as temperature was concerned, this was we found that our predictions sharpened up when we used not just raw temperature, but something called heating degree days. Geographers define something called heating degree days, which is the difference between the temperature and the comfort level, which varies around the country. But if you can find that comfort level, and you talked about it with a curve, that if you take that off the temperature, then you get some measure of the demand. And we found that sharpened up our estimates. Have you tried that?
No, we haven't. Can I talk to you about it later?
Okay, so I think we need to move on. Now, can you hand over the microphone to Mark, please? And Andrew, Richard.